Hello everyone, today I'll be talking about properties of projections. This is material from 6.3 of the text. So this will be kind of a continuation of what we talked about in the last lecture. Let me recall the setting here. Suppose W is a subspace of Rn with, let's say you give me an orthogonal basis, right? That's important. It's an orthogonal basis. Let's call it U1 through UP. And then you give me any other vector, right? So let's let y be any vector in Rn. So maybe I'll try to draw my usual picture here. So suppose we got u1 here and u2, and this is an orthogonal basis for the subspace that it spans. So let's say it looks something like this. And then I've got this other vector, let's call it y. So y is this, it could be any vector. Let's say it's this vector that's kind of coming out of the plane. We can project it down. Let's say it looks like this when I project. This is called y hat usually. So this is my subspace W. I've got the orthogonal basis for W, and then I've got this vector y. So fact one, I want to write down a couple of things that we maybe touched on before, but I want to make explicit here. Fact one is that y can be written in a unique way, so uniquely as, let me write it like this, so y is going to be something plus something. And the point is that this guy will be a vector in the subspace W, and this vector will be a vector in the orthogonal complement, W perp. Right, so y hat, this vector y hat, that was the projection. Okay, so we talked about that last time. Now the z we also mentioned last time, that'll be this, using this other color, that's this vector here. It's really the third leg of this triangle, right? But since we want to think about it as a vector, we want to put its, tail at the origin, and so that vector z will be the other vector that I get. And notice that it is perpendicular to W, right? If you think about it, this projection will always have this property that the third leg of the triangle will be this thing that's orthogonal to the subspace you're projecting on. Okay, so actually, let me just write down. Last time we saw that what this y hat is. So this is the projection of y onto W. So what was the formula here? This was this y dot u1 divided by u1 dot u1. Right, that's a number. We scale u1 by that. And we do that for every vector. So y dot up divided by up dot up. That's a number. We scale up by that. That's what we talked about last time, this formula. And what is z? Well, it's going to be, right, it's going to be y minus y hat. So if you go back to your picture here, we see that z plus y hat, right, is y. If you take the tail of z and put its tail at the head of y hat, you get to y. And if you solve for z, you get this. Okay, so that'll be the, these are the formulas for these two vectors you get. The point is that any vector y can be written uniquely as something in W plus something in W perp. And that's how you actually get those vectors. Okay, so maybe fact two I want to mention here for you guys. Fact two. Well, what happens if y is in W? Then, what happens when you take? Let me go back to my picture here. If you actually happen to take a vector y that sat in the plane. Well, when I project it, right, it's going to do nothing. So what I get is that y hat equals y, okay? And in fact, in this case, z is the 0 vector, okay? And that should make sense again, right? So if I take that vector y and I happen to pick a vector that was already in the subspace, then projection will just give me that vector back. It'll give me y as the projection. Okay, let's see, fact three is kind of a geometric interpretation of projection. So this will be important as we move forward the last couple weeks of class. So let me say this in words. Maybe y hat is the point in W closest to y. And what do I mean by that? Well, if I take y minus y hat, if I take the distance between y and y hat, which is, of course, the length of this vector, this is going to be less than the distance between y and any vector v And this will hold true for any vector v in W where v is not equal to y hat. Okay, so what am I trying to say here? Remember, this is the distance, right? This formula here is the distance between these two vectors. And so maybe try to recreate this picture a little bit. So what I'm saying here is that if this was the vector y that I was projecting, right, I'm projecting onto this subspace W, here's my vector y hat. And if I take any other vector, say z, or I called it v, right? So what I'm seeing here is that the distance between y and y hat is the length of that dashed line, and it's going to be shorter than any other, the distance between any other vector in W with y. Okay, so among all the vectors in W, this projection is the one that's closest to y. So y is the point in W closest to, sorry, y hat is the point in W closest to y. Okay, so that's a nice way to think about projection, is it gets you the thing in W closest to the vector you're projecting. Okay, so maybe fact 4 I'll put here is, again, it's kind of a hodgepodge of things here, but just want to point out one more nice thing that happens when we have kind of even more special basis. So if U1 UP is an orthonormal, basis for W, then, well, let's go back to our formula here, right? We know we have a formula for projection of a vector, right? It was this guy here. Now notice, remember, orthonormal means that not only is this an orthogonal collection, but each vector has length 1. So when I go to my formula here, I'm taking these dot products, right? Each vector has length 1, so these all become 1. These denominators all become 1, they all disappear. So what we get is that y hat is actually equal to, well, it's going to be y dot u1, right, divided by 1. It's gone now. It's just that guy. So the next one would be y dot u2 times u2 plus y dot up. Scale the vector up by that number. Okay. Now again, orthonormal, remember, means that, so I'll just write it here. This means that you're orthogonal and the length of ui equals 1 for all I. Okay, so that's kind of fact 2 there. Or sorry, fact 4. Actually, let me say more about fact 4. So if you think about it, this actually has a nice matrix multiplication interpretation. So let's see, if we let U be the matrix that I get by just putting those into a, as columns in the matrix, then if you think about it, this formula here actually can be written as a matrix multiplication. So this will actually be U times U transpose times Y. Okay, so let's unravel this a little bit. So this matrix, right, these are all vectors in Rn. So this is a what? N by P matrix. So U times U transpose will be, well, what is this? This is N by P times a P by N. So let me just say that U times U transpose is an N by N matrix. Okay? And so what I'm seeing here is that this matrix is an N by N matrix, and what it does is it eats a vector Y and spits out the projection onto the subspace. And that's nice, right? You can use this matrix U transpose to project any vector Y. Right? So what's nice is that you have this matrix now. It's an N by N matrix, and you can just feed it any vector you want, and it'll give you the projection when you multiply it by that given vector. Maybe just to give you an example of kind of, one of what these might look like. So I wrote down one here. So here's a 3 by 2 example. So this is a matrix. You can check, well, it's got 2 columns. Okay, so we want to think about these 2 vectors as a basis, or an orthonormal basis for a plane in R3, right? So that picture we were drawing. And you can check that it's an orthogonal set, but it also, these vectors all have length 1, if you look at the length of each of these columns. And so let me just end with a couple other observations here. well, let me just say it this way. A matrix U with orthonormal columns has many nice properties. So, so one nice property is that you can get this kind of projection matrix out of it. But I think we also saw last time, or we maybe discussed on a worksheet, that if you take U times, well, if you take now U transpose times U, so what is this going to be? This is going to be, right, U transpose now was P by N, and this is N by P. This will be a P by P matrix. It turns out that this is actually the identity matrix on P. And maybe something for you guys to think about, or we might talk about on a worksheet. And then one last definition I want to give you guys here is that an n by n matrix, so a square matrix with orthonormal columns, is called an orthogonal matrix. Okay, so this is a little bit maybe unfortunate naming here. So it's kind of funny that a matrix with orthonormal columns, you call it an orthogonal matrix, right, if it's square. So a square matrix with orthonormal columns will be an orthogonal matrix. Of course, one example of this is the identity, but there's others. And anyway, so we've seen now that those kind of show up in nature. Next time we'll talk more about projections, some more applications, so we'll see you then.